All right, welcome to lesson 9.5. We're looking at the composition of functions today. So I think that this is the most important combination of functions that we look at in this course. We're going to look at this type of combination again in calculus if you're taking that course next semester. So for composition of functions, if you just take a look on page 545 in your textbook, there's this introduction. So this is page 545, this introduction talking about like why we might use something like this. So they got just a simple example here about forest fires that spread in a roughly circular pattern. And so we know that the area burned will depend on the radius of the fire, but the radius is going to increase over time. So the radius depends on time. So we've got kind of like this domino effect here. So we've got the area depends on the radius. So the area in terms of radius is pi r squared. And then we also have that the radius in terms of time is 0.5 times t. So I can combine these functions, and that's what what we're thinking about with composition of functions, is that I've got my first function, which is the radius function here, and I'm going to put an input into that function. I'm going to call that x1, and it's a time input in this example. And then what's going to pop out of that function, that's my first output. So we call our outputs y's. But we're going to turn that in. We're just going to, instead of calling it y1, now I'm going to call it the input to the second function. Now the second function is the area function, and then I'll pop out my second output will be the y2. And the box is just like the calculation that I'm going to do to the value. So I put the first input in, pop it out, and then it transforms into the second input, and then I get my second output. So we want to be able to combine these two different functions, and we use a composition function for that. So let's take a look at the notation. Here it is for a composition of functions. I'm going to say f of g of x is how I would read this, f of g of x. And here you can see it's really just substituting g at x into f at x. So I'm putting g at x into f. Vice versa, if I were to write g of f of x, that means that I'm putting f at x into the g function. And so you can think about like, well, which function is being completed first here? It's the one on the right. So always this guy on the right is the one that's completed first. So if I was thinking about that forest fire example, the g at x would be the radius. So first I would plug in the time, I would get the answer for the radius, and then I would plug that answer into the area function. Or over here, I'd get the time, I'd plug it into the radius function, and then I'd take that answer and plug it into the area function. So I'm starting on the very inside bracket, working my way kind of back out. All right, so let's take a look at an example just with a couple of equations. So we've got f at x is 2x minus 3, a linear, and g at x is x squared, so a parabola. And we're going to calculate first what is f of g of 4. So first I'm going to just think about, well, what does that even mean? And this is just like a tiny open circle here. So f of g of 4, and notice that that open circle is in the midline. It's not on the bottom or at the top. It's right in the middle of f and g. Just like where you would write a time sign or a plus sign. So this is the same of f of g of 4. And so what that means is first we're going to figure out what is g at 4, and then we're going to put that answer as the input into the f function. So some people will do that right in line with the work here, or some people like to go off to the side and in a second column figure out, well, what is g at 4? So to do that, I'm going to take the number 4 and replace all the x's in g with a 4. So I'm subbing in 4 for x, and I get the answer 16. And then I can come back here, and now I know that g at 4 is 16. So everywhere I see a g at 4, I'm going to replace it with a 16. So now I have f at 16. And this tells me put the input 16 into the f function. So everywhere I see an x there, I'm going to replace it with a 16. And so I get 32 minus 3, or 29. So now we're going to take a look at, well, what is g of f of 4? So similar to our last example, but the letters are switched. So what difference does it make? So g of f of 4, that means we're going to plug 4 into the f function and then take that answer and plug it into the g function. So starting on the inside, working our way out. Again, you could go off to the side and figure out what f at 4 is, so I could write that off to the side. Or if you'd rather, and if this is a preference, I don't care what you do here, I'm going to plug 4 into the f function and I'm going to do it inside the brackets. So it's 2 times the x value, so 2 times 4 minus 3. And so I've got g at 8 minus 3 or g at 5. So either way, I've shown my work of substituting the 4 into the interior function. Here I've shown it off to the side of my rough work, and here I've shown it inside the brackets of my outer function. And g at 5, now I'm going to plug 5 into the g function, so replacing the x there with a 5. All right, so part C, does order matter? So, is it true that f of g of x is the same as g of f at x? Well, we can see in our example it's definitely not true. I got 29 over here and 25 over here. So does order matter? Yes, it does. And does f of g equal g of f? No. It does sometimes. It is very rarely true, though. We're actually going to look at an example at the end of this lesson for when it is true. All right, so let's state the equation then for f of g of x. Instead of plugging in a specific number for x, what would the equation be in general if I just leave the x? So again, I'm going to start off by saying that f of g of x is equal to f of g of x. And now I'm just going to replace the entire g at x with the equation for g at x. So instead of g at x, I'm going to write x squared. That's the equation for it. And now it says take x squared. Replace all the x's in f with an x squared. So instead of writing 2 times x, I'm going to write 2 times x squared and then minus 3. Now we're going to take a look at the, and that's in simplest form, right? There's nothing for me to expand there, or factor if I prefer factored form. So next we've got g of f of x. And I'm going to plug in, so I've got g of f of x. So I'm going to plug in the f at x equation into the g. So the f at x, and first I'm going to replace that. That's 2x minus 3. And I'm going to plug that whole expression in for each x in g. So it's saying wherever there's an x in brackets, put a 2x minus 3 instead. And then the g function, the squaring, goes on the outside of that. Now, is this the same as what I got over here? No. If I were to think about expanding this out, I would have 2x times another bracket with a 2x at the front, so that would be 4x squared. And then I would have 2x times negative 3 and negative 3 times 2x. So I'd have negative 6x minus another 6x, or negative 12x. And then I'd have negative 3 times negative 3, so positive 9. So definitely we can see that these equations are not the same. This one being in factored form we might like better. This one in standard form depends what you want to do with it, I guess. In the next section, we're going to talk about domains. So just for a second, I'm going to come back and talk about these domains. For the domain of f of g, we can see here that this is a parabola. It opens up and it's been shifted down, but a parabola has the domain of x belongs to a set of real numbers. This guy is also a parabola. So also the domain of x belongs to the set of real numbers. So this is kind of a special case where it's a really simple domain, and that's because we started off with two pretty simple equations. The domain of f at x is the set of real numbers, and the domain of g at x is also the set of real numbers. So that's why we're seeing these nice simple domains here. In general, though, to come up with the domain of f of g of x, well, first you have to think about, well, what am I doing? First, I would be plugging the x into g. So what I'm going to look at first is the x values that are in the domain of g. And that's because I'm first plugging x into g. But then the next piece is I'm going to take those g answers and I'm going to plug them into f. So I need g at x, that's the y values of g at x, to be in the domain of f. So there's a kind of a second piece here. So another way to say this is that the set of x values that give a y value in the first function g and that y value is also an acceptable x value in the second function f. So it's kind of complicated. We're going to take a look at a couple of examples here. Okay, so for my first example, for my second example, I've got two equations again. This time we're dealing with a radical and a rational function. So kind of mixing it up, getting a little bit trickier here. First, it says find f at g. So what they mean by that is find f of g of x. Okay, so that means take the g at x equation and put it into the f equation. So g at x, that's 1 over x. So everywhere I see an x in the f function, I'm going to replace it with 1 over x. Okay. Now we're going to find g of f of x. So going the opposite way, this time I'm going to take the f function and plug it into the g function. So the f function is root of x plus 2. And so that says take the x is in the denominator for g, and replace it with the whole f function. And there we go. All right, so there's nothing I can do to simplify those functions. Now we're going to talk about, well, what is the domain? So again, the first thing I look at is the first function, which remember actually always comes second in the equation. So the interior function here is g. So I'm going to look at g first. Now for g, when I'm looking at 1 over x, I'm going to ask myself, like, what's the domain of this? And the domain tells me that x cannot be equal to 0. This is just my rough work, so I'm not going to worry about the set of, that x belongs to the set of real numbers and all that, because right now I'm just kind of trying to piece it together. So I've looked at that, so I'm going to remember that x cannot equal 0. I can't plug that in. And then the next thing I'm going to do is I'm going to look at the actual equation for f of g. Okay, so that equation tells me that I've got the square root of something. Now I know that I can't take the square root of a negative. So it says whatever you're taking the square root of has to be positive or equal to 0, right? It can be either one of those. So a positive number or equal to 0. So I'm just taking the thing under the root and saying it's got to be greater than or equal to 0. And now I'm just going to solve this so that I've got x on one side by itself. So I can bring the 2 over and subtract it. But now I'm kind of stuck. So you might remember that when we multiply across an inequality sign, a greater than sign or less than sign, if I'm multiplying by a negative number, I have to flip the sign. So let's say I take this x and I multiply it up to the other side. Well, I don't know if it's positive or negative, so I'm not really quite sure what to do with this sign. So since I can't multiply by x, I'm going to look at the graph instead. So I know that the graph of 1 over x, this is one of my parent functions from grade 11. It looks like this, right? And what I'm interested in is where is it across from -2? This is just a different strategy for solving an inequality, right? Is where is the graph above -2? And so I want to know where this value is right here. And if we remember reciprocals, so if I ended up with the answer -2, what did I plug into 1 over x? I plugged in -1/2, right? It's going to have to be the flip of each other because it's the reciprocal graph. So what I've got then for my two solutions is the graph is above -2 when I'm less than -1/2 or equal to, right? Because this is an or equal to. So I'm going to include that point. Or the other part of the graph that's above -2 is this section here. So that section is x is greater than 0. Now I'm not going to say or equal to 0 because 0 is a vertical asymptote, so I can't include that. So I've got my two different solutions. So now what I'm going to do is combine this answer here with this answer here. I'm going to think about, well, what's the overlap of these guys here? So if this had been greater than or equal to 0, I would have to take away the equal to 0 because this guy says you can't equal 0. But I actually already have this statement, x can't equal 0, it's already implied here with x is strictly greater than 0. So I've actually got my entire domain right here. And I'm just copying it into my domain set notation. All right, now we're going to take a look at the domain of g of f. So again, we start with the interior function. That's the second one in the equation. And so I'm going up and I'm taking a look at my f equation. That's the square root of x plus 2. So I know that I can only take the square root of positive numbers or 0. So that tells me that that thing under the square root has to be greater than or equal to 0. And then I can rearrange this and solve for x. So I know that x has to be greater than or equal to negative 2. So now I'm going to look at the whole function, and I've already come up with this equation here. So looking at g of f, 1 over the square root of x plus 2, what I know is that the denominator can't equal 0. Right? So when I'm looking at a root function, I know that the thing under the root has to be greater than 0. When I'm looking at a rational function, the denominator can't equal 0. So here what I get is root of x plus 2 can't equal 0. Now I'm not going to worry about the fact that I can't take the square root of a negative, even though that is implied here. It's because I've already dealt with that when I looked at f on its own. So I've already taken care of the root in this function. If you hadn't, then you would have to consider that. Now I'm going to solve here for x. So I've got the square root. To move it to the other side, I'm going to square both sides, and I get x plus 2 can't equal 0. And then I'm going to move the 2 over and subtract it. And I see that x cannot equal negative 2. And now I'm going to combine these two statements. So I've got that x has to be greater than or equal to negative 2, but x can't equal negative 2. So that means that x is strictly greater than negative 2. All right, for our next question, we're going to take a look at inverses. Now, it might have been a while since you've thought about inverses, so I'm just going to remind you that to find an inverse equation, we swap the x and the y variables, and then we rearrange until it looks like y equals. Okay, so I'm going to take my equation. This is y equals log x, and I'm going to swap it to find the inverse. So the inverse will be x equals log y. Now I want to be able to rearrange this for y. So remember, when you want to rearrange a log, we're going to use that pattern that log base b of a is equal to c. Remember, b is the base, so b is the base, and the log equals the exponents. The exponent is c, and that's going to equal a. A is the power. So we're going to rearrange this one over here. Remember that if there is no base showing, there is a little invisible 10 down there. So the base is 10, the log equals the exponent, and then the power is y. And now we've got our f inverse function, so I'm just replacing the y with an f inverse notation, and that's 10 to the power of x. Okay, so I've got my two equations, f at x and my f inverse of x. For part B now we're going to find f composed with f inverse composed with x. So that means plug the inverse function into f. So the inverse function is 10 to the power of x, and I'll plug that in to my log function. So log x, but now I'm plugging 10 to the power of x in for all the x's. So now what I have here is log base 10. Remember, that means what is the exponent on 10 that gives me the answer 10 to the power of x. So this is saying what is the exponent on 10 that gives me 10 to the power of x? Well, x. It's pretty obvious when we write it like that. And so if I take f and I compose it with its inverse, I actually get the input back out. Now we're going to check what happens when I put the function into the inverse. So this time I'm going to put the function in. The function was log x. And I'm substituting that into the inverse function. So remember, the inverse function was 10 to the power of the input. So 10 to the power of log x for us. Now, you might remember that we have a log law that says if I have a to the power of log base a of b, then the base a here and the log base a and the exponent kind of like cancel out and the b comes down. So when I look at this guy, I've got 10 to the power of log base 10, remember there's an invisible 10 there, of x. And so I'm going to use this log law to say that the answer of this is also x. So if I put the function into the inverse with the input x, I get the output x. And so in general, this is going to work for any function and its inverse pair. If I take an input x and put it into the composition of the function with its inverse, I will get x back as the output. And that's going to be true as long as x is in the domain of the inverse. And then vice versa, if I put x into the function and then take that answer and put it into the inverse function, I'll get x back out. Hopefully this makes sense if you remember what an inverse function does. It does the opposite of what the original function does. All right, that's it for today's lesson. Have fun with the homework.